So if you have questions, ask them. Welcome to workshop on geometry of spaces with upper and lower curvature bounds. This is a part of a thematic program on non-smooth Riemannian Lorentzian geometry here at Fields. Before we start, I have one personal announcement request. There is no mask mandate here, as you probably have seen announcements, but we would like to ask you to please wear masks. I brought some today. If you don't have yours, please take one. COVID is not over. There is COVID here at Fields. Different cases. A lot of people in a large room. That's a great way to get somebody sick. Okay. So thank you.
Thank you.
All right. Also, there is a. I mean, I have a few here, but there is a summit. Okay. Thanks. Okay. All right, but yes, thank you. Okay, well, let me introduce the first speaker. That's Professor Kingshook Biswas from Institute for Indian Statistical Institute in Calcutta. Unfortunately, Professor Biswas is cannot join us in person, but so he'll talk about quasi-metric antipodal spaces and maximal Gromov hyperbolic spaces. Thank you. Please go ahead.
Okay. So thank you very much to the organizers, Professors Kapovich, Searle, and Schroeder for the invitation. I'm sorry I couldn't make it in person, but I would like to thank you very much for allowing me to give this talk online. So let me start. So let me recall the definition of a quasi-metric. It's given a set Z, a function rho on Z cross Z is called a quasi-metric. If, like a metric, it satisfies a positivity axiom, a symmetry axiom, and instead of the triangle inequality, it satisfies what we could call the quasi-metric inequality. So there exists a constant k greater than or equal to 1, such that rho of xi eta is less than or equal to k times the maximum of rho xi zeta and rho zeta eta for every triple of points xi zeta eta in Z. So then we say that rho is a k quasi-metric. A one quasi-metric is called an ultrametric, and any metric is a two quasi-metric. Now, given a quasi-metric space Z rho with at least 4 points, we can define the cross ratio with respect to rho of a quadruple of distinct points by the usual formula mimicking the Euclidean cross ratio in Rn. It's a product of rho distances divided by a product of rho distances. So it's a positive function on the set of quadruples of distinct points. So we say that two quasi-metrics rho 1, rho 2 on Z are Moebius equivalent if they have the same cross ratios. And we say that a homeomorphism F between quasi-metric spaces is Moebius if it preserves cross ratios. So the main example will come from cat-1 spaces. So let me just recall the definition of the Gromov inner product in a metric space. So the Gromov inner product of 2 points yz with respect to x is half of the distance xy plus the distance xz minus the distance yz. So in this picture, this distance plus this distance minus this distance. So if you do this in a tree, you get a picture like this. And for a tree, these sides cancel out. And the Gromov inner product is just the length of the common segment of the geodesics from x to y and from x to z. So it measures how long the geodesics x to y and x to z stay close to each other. So now suppose X is a cat minus 1 space with boundary del X. Then it's a fact that for any 2 points in the boundary, xi and eta, the limit of Gromov inner products yz with respect to X, as y converges to xi and z converges to eta, this limit exists. And this is defined to be the Gromov inner product of xi eta with respect to X. And this is equal to plus infinity if and only if xi is equal to eta. So this leads us to the definition of what's called the visual metric on the boundary based at a point little x in X. So rho x of xi eta is defined to be e to the minus Gromov inner product xi eta with respect to X. So Buddo showed that this is a metric. So, I mean, one has to verify the triangle inequality. So for a cat minus 1 space, this satisfies the triangle inequality. So for example, if you take X to be the real hyperbolic space Hn, and you take Hn, the ball model, the unit ball model, Bn, then if you take the visual metric with respect to the origin, rho naught, then this turns out to be just half times the caudal metric on the boundary of the ball, which is the n-1 sphere. Okay, so the visual metric you can think of as a generalization of the caudal metric on the boundary of the ball, the hyperbolic unit ball. And if X is a tree, then this visual metric is an ultrametric. Okay. Now, I want to talk about a very important property of these visual metrics, which is called the antipodal property. So first note that since Gromov inner products are non-negative, the visual metrics are bounded above by 1. And the visual distance between 2 points xi eta with respect to X, this is 1 if and only if X belongs to the unique bi-infinite geodesic joining the boundary points xi and eta. So now suppose X is geodesically complete. So this means that any geodesic in X can be extended to a bi-infinite geodesic defined for all time. Then if I take any boundary point xi, we have a geodesic ray from X to xi. Since X is geodesically complete, we can extend this geodesic ray to a bi-infinite geodesic, xi comma eta. So this passes through X, and so you get some other point eta in boundary X, such that rho x of xi eta is equal to 1. So this means that rho x is antipodal. What that means is that the metric rho x has diameter 1, and every point xi in boundary X has an antipode. That means a point eta in boundary X such that rho x of xi eta is equal to 1. Okay, so this is the antipodal property for geodesically complete cat minus 1 spaces. Okay. Now, if we look at the cross ratio of a visual metric, it turns out that all these visual metrics, rho x, as X varies over base points in this cat minus 1 space, these are all Moebius equivalent to each other. So the proof of that is just this picture, where if you take the definition of the cross ratio, it's a product of visual distances divided by a product of visual distances. So visual distances are exponentials of minus the Gromov inner product. So you'll get 4 Gromov inner products. So that will give you 4 triangles based at X. And the sides of those triangles come with different signs. And what happens is all the sides which start from X, these come with both a plus and a minus. So these sides cancel out. So the cross ratio that you're left with only depends on these distances. I mean, these are to be understood as limits as you take points inside converging to the boundary points. So this is independent of X. So that means that there is a canonical cross ratio on the boundary of a cat-1 space, and you can express it in terms of distances in X as a limit of an alternating sum of distances in X. Okay. So now, since cat-1 spaces, the boundary has a canonical cross ratio, we can define an embedding between boundaries of cat-1 spaces to be Moebius if it preserves cross ratios. And since cross ratios are given in terms of distances in the inside, it's easy to see that any isometric embedding between cat-1 spaces extends to a Moebius embedding between their boundaries. So a natural question is the converse. Given cat-1 spaces xy and f from boundary x to boundary y, a Moebius embedding, does f extend to an isometric embedding from x to y? So for example, if you take x and y both to be the real hyperbolic space and you take the ball model, then as we've seen, the visual metric is just half times the caudal metric. And so the cross ratio is just going to be the Euclidean cross ratio on Sn-1. And then it's a classical fact that Moebius maps from the boundary of the unit ball to the boundary of the unit ball, they extend to isometries from Bn to Bn. So in this example, this is a well-known classical fact that Moebius maps extend to isometries. And this fact is useful in various rigidity theorems, for example, Mostow rigidity and pattern rigidity. But the main motivation for this problem of extending Moebius maps to isometries is the marked length spectrum rigidity problem. So suppose XY are complete simply connected Riemannian manifolds of sectional curvature bounded above by -1. So they're cat-1 spaces. So if any Moebius map from boundary X to boundary Y extends to an isometry F from X to Y, then the marked length spectrum rigidity conjecture is true. Okay, so a positive answer to this question of extending Moebius maps also gives a positive answer to the marked length spectrum problem. So I won't talk more about the marked length spectrum problem, but this is the main motivation for this problem. So let me give some results on this problem. So Bourdeau showed that if X is a rank 1 symmetric space of non-compact type, where the metric is normalized so that the maximum of the sectional curvature is equal to -1, and Y is any cat-1 space, then any Moebius embedding from boundary X to boundary Y extends to an isometric embedding from X to Y. So for rank 1 symmetric spaces, we have a good answer. And for a general domain, we have the following. So if XY are proper and geodesically complete cat-1 spaces, and F from boundary X to boundary Y is a Moebius homeomorphism, then F extends to a locally half Holder continuous 1, log2 quasi-isometry from X to Y, and the image is half log2 dense in Y. So here the multiplicative constant of the quasi-isometry is 1, and the additive constant is log2, independent of the spaces X and Y. And if you have a lower curvature bound, then you can improve this result. So if X and Y are complete simply connected.
Sorry, question?
Yes. Yes.
Is this a sharp bound?
Well, you want to show that actually it extends to an isometry. So you would hope that it's not sharp. You would hope that it should be an isometry, not a quasi-isometry. Yeah. So
okay.
The conjecture is that it should be an isometry. So here's something a bit sharper. If you have a lower curvature bound, so suppose X and Y are manifolds, complete and simply connected, with pinched negative curvature. So between -b² and -1. So there's a lower curvature bound. Then the Moebius map, it extends to a 1, 1 - 1 over b log2 quasi-isometry. from X to Y. And this extension is surjective. So here note that the additive constant in the quasi-isometry, this tends to 0 as B tends to 1. So as the pinching becomes smaller, the result is sharper. In particular, this says that for real hyperbolic spaces, you get an isometric extension when B is equal to 1. Okay, so let me give some more results. So suppose X is a complete simply connected Riemannian manifold with sectional curvature less than or equal to -1. So G0 is the metric on X. And let G be another Riemannian metric on X such that G is equal to G0 outside a ball B, and such that G also has sectional curvature less than or equal to -1. Then if I look at the identity map from X with the metric G0 to X with the metric G, it's easy to see this is a quasi-isometry. So this extends to a homeomorphism, identity hat G0, G, from boundary X with respect to G0 to boundary X with respect to G. Then we have the following infinitesimal rigidity theorem. So let GT be a smooth family of Riemannian metrics on X such that all the metrics GT are equal to G0 outside a fixed ball B. And all of the metrics GT have sectional curvature less than or equal to -1 on all of X. Then suppose that the boundary maps from boundary X with respect to G0 to boundary X with respect to GT, suppose all of these boundary maps are Moebius for all t in 0, 1. Then all of these boundary maps extend to isometries from X with the metric G0 to X with the metric GT. Okay. So that's an infinitesimal rigidity theorem. We also have a local rigidity theorem. So let B be a closed ball in X. Then there exists epsilon only depending on this ball, such that for any metric G which satisfies the following: G is equal to G0 outside the ball B. The sectional curvature of G is less than or equal to -1 on X. The C2 norm of G minus G0 on this ball B is less than epsilon. And the volume of the ball B is the same for G and G0. Then if the boundary map from boundary X with respect to G0 to boundary X with respect to G is Moebius, then this boundary map extends to an isometry from X, G0 to X, G. So this is a local rigidity theorem. Now, much earlier, Kurnair showed that for trees, we have a complete answer also. So if X, Y are proper geodesically complete trees, and F from boundary X to boundary Y is a Moebius homeomorphism, then F extends to an isometry from X to Y. And taking this further, Barer and Schroeder showed that actually the functor sending a tree to its boundary equipped with a visual metric, which is, as we noted, an ultrametric. This defines an equivalence of categories between proper geodesically complete trees, where the morphisms are isometries, and ultrametric antipodal spaces. So ultrametric satisfying the antipodal property, where the morphisms are Moebius homeomorphisms. Okay. So to prove this, what Barer and Schroeder did, they constructed a proper geodesically complete tree from an ultrametric antipodal space. And so the natural question is, what can we do the same for cat-1 spaces? Given a proper geodesically complete cat-1 space, can we reconstruct the space X from the boundary equipped with its cross ratio? And the answer is almost. So we can construct a proper geodesically complete Gromov hyperbolic space M of boundary X such that X embeds isometrically into M of del X, and the image is half log 2 dense in M of del X. And any Moebius homeomorphism between boundaries del X to del Y extends to an isometry f star from m del x to m del y. So this is a functorial construction. And this leads to what's called a circumcenter extension of Moebius maps. So suppose xy are proper geodesically complete cat-1 spaces, and F is a Moebius homeomorphism between their boundaries. So then we have this isometry F star from these Gromov hyperbolic spaces m del x to m del y. And now we can do the following. For each point little x in x, you think of x as sitting inside m del x. X sits isometrically inside m del x. So for each x, there is a unique point y in y, which is nearest to the point f star of x in m of del y. Okay, and so the circumcenter extension, capital F from x to y, is given by putting capital F of x equal to y. Okay? And the fact that y is half log 2 dense inside m del y implies that F is a 1 log 2 quasi-isometry. So this is how you prove that you get a 1 log 2 quasi-isometric extension. So this picture should make it clear what's happening. Here, x is sitting isometrically embedded into m of del x. Here, y is sitting isometrically embedded into m of del y. We have this isometry f star from the big spaces m del x to m del y. So x here maps to another space here, f star of x, with the same boundary as y. And so now what we're doing is we take a point little x, we look at f star of little x, that's this point, and then we take a nearest point projection to the subspace y. So that is the point capital F of x. So this is the circumcenter extension. And this distance between the nearest point and the point f star x, this is less than or equal to half log 2 here. And if I take a point y, then the distance between f star y and capital F of y, this is less than or equal to half log 2. And so then it follows that capital F is a 1 log 2 quasi-isometry. Okay, so now we want to generalize what we have for cat-1 spaces to Gromov hyperbolic spaces. Because as we've seen just now, Gromov hyperbolic spaces naturally occur when trying to reconstruct the space from its boundary. So a Gromov hyperbolic space X is said to be boundary continuous if for any point little x in X, the Gromov inner product with respect to X, this extends continuously to the boundary. So as we've already stated, cat-1 spaces are examples of boundary continuous Gromov hyperbolic spaces. And in fact, one can show that cat-0 Gromov hyperbolic spaces are also examples of boundary continuous spaces. So this gives a much larger class of examples. So for example, Gromov hyperbolic cat-0 cube complexes, these would be boundary continuous. So for a boundary continuous space, we can imitate what we did for a cat-1 space. You define rho x of xi eta to be e to the minus Gromov inner product xi eta with respect to x. Now, this is no longer a metric, rather it is a quasi-metric. Okay, so we call this the visual quasi-metric. And it's important to note that this is a continuous quasi-metric on boundary x cross boundary x. And just like for cat-1 spaces, the same picture will tell you that all the visual quasi-metrics are Moebius equivalent to each other. So there is a canonical cross ratio on the boundary of a boundary continuous Gromov hyperbolic space. So now suppose X is a proper geodesically complete boundary continuous Gromov hyperbolic space. So in short, we will call such spaces good Gromov hyperbolic spaces. Then, since X is proper, boundary X is compact, And as we saw earlier, geodesic completeness implies that the visual quasi-metrics, rho x, these are all antipodal. And therefore, boundary x equipped with any visual quasi-metric is a quasi-metric antipodal space. So this means a compact space equipped with a continuous quasi-metric, which is antipodal. So now, suppose we start with a quasi-metric antipodal space, Z, rho naught. Then we can look for hyperbolic fillings of this quasi-metric antipodal space. So we define a good filling of Z to be a pair X, F, where X is a good Gromov hyperbolic space, and F from boundary X to Z is a Moebius homeomorphism. Okay. So this is a good filling. And then two good fillings, X, F and Y, G, are equivalent if the natural Moebius map between their boundaries, G inverse F from boundary X to boundary Y, this extends to an isometry from X to Y. So then we can look at Fz, which is the set of good fillings of Z modulo this equivalence. Now this set, we can define a partial ordering on this set. So XF is less than or equal to YG if, again, the Moebius map G inverse F from boundary X to boundary Y, this extends to an isometric embedding from X into Y. Okay, so X sits inside Y. It is a smaller filling than Y. Okay. And then it's not hard to show that this set of good fillings with this relation is a partially ordered set. Okay, so this is a partial order. So then there are natural questions. So first of all, is the set of good fillings non-empty? So does every quasi-metric antipodal space have a good filling? In that case, if so, does the set of good fillings have maximal elements? So does this partially ordered set have maximal fillings? And if there are maximal elements, then in fact, is there a unique maximal element, MZ, in Fz? And if there is a unique maximal element, is it true that every other filling X is less than or equal to MZ? Okay, so these are some natural questions. And it turns out the answer to all of these questions is yes. Okay. So in fact, what we're going to describe the construction of this maximal filling MZ. In fact, we will do it for a more general class of spaces called antipodal spaces. So I'll come to that. So let Z be a compact metrizable space. Then a separating function on Z is a continuous function rho naught on Z cross Z, which just satisfies symmetry and positivity. So we're not requiring any triangle inequality, any quasi-metric inequality, just symmetry and positivity. Such a function is called a separating function. So a separating function, rho naught, will be called an antipodal function if, first of all, rho naught of xi eta is less than or equal to 1 for all xi eta. And secondly, every point xi has an antipode. That means a point eta such that rho naught of xi eta is equal to 1. Okay, so this is an antipodal function. So note, we're not requiring any triangle inequality or quasi-metric inequality. We'll get a rich theory just from the antipodal property. So Z equipped with an antipodal function rho naught is called an antipodal space. Okay. Now, I need to say something about what's called the geometric mean value theorem. So for a separating function, we can define its cross ratio by the same formula as before. And we can, as before, define Moebius equivalence of separating functions. So then the geometric mean value theorem says the following, that two separating functions, rho1, rho2, are Moebius equivalent if and only if there exists a positive continuous function phi on Z such that this geometric mean value theorem holds. So ρ2 of xi eta squared is equal to phi xi into phi eta into ρ1 of xi eta squared. Okay. So the separating functions will be Moebius equivalent if and only if you have such a positive continuous function phi such that this equality holds. Okay. So such a function, if it exists, is unique. And we call this function phi the derivative of ρ2 with respect to ρ1. And we denote it by d ρ2 by d ρ1. Okay, the reason it's called a derivative is because at least if I take a non-isolated point of Z, say xi, then phi of xi, it's not hard to see, it's going to equal the limit as eta tends to xi of the ratio ρ2 xi eta divided by ρ1 xi eta. So in that sense, it is a derivative. It's a conformal factor between the two separating functions ρ1 and ρ2. Now, we're going to define certain metric spaces. So let Z ρ0 be an antipodal space. Okay, so ρ0 is an antipodal function on Z. Then the unrestricted Moebius space UM of Z, this is the metric space UM of Z. This is the set of ρ such that ρ is a separating function which is Moebius equivalent to ρ0. So what is the metric on this set? The metric is the following. The distance between ρ1, ρ2 is equal to the sup norm of the log of the derivative d ρ2 by d ρ1. Okay. So this turns out to be a metric on this set of separating functions, Moebius equivalent to ρ0. And in fact, as a metric space, this UM of Z, this is actually isometric to the Banach space of continuous functions on Z, CZ, equipped with the sup norm. The isometry is just the map which sends ρ to the log of the derivative d ρ by d ρ0. So this map is an isometry. And the inverse of this isometry is given by a map E from CZ to UMZ, which is defined as follows. For any continuous function tau in CZ, we define a separating function ρ equal to E of tau in the unrestricted Moebius space UMZ by ρ of xi eta squared is defined to be e to the tau xi, e to the tau eta into ρ0 of xi eta squared. Okay. So this is a separating function such that the log of the derivative d ρ by d ρ0 is equal to the given continuous function tau. So this is the inverse of the isometry. Now we can come to the main definition of the talk, which is the Moebius space MZ. So suppose Z ρ0 is an antipodal space. So then the Moebius space MZ is defined to be the metric space. MZ is the set of ρ in the unrestricted Moebius space. So that means separating functions Moebius equivalent to ρ0 such that ρ is also an antipodal function. Okay. So Moebius equivalent separating functions which are also antipodal. Okay. And the metric is the same as before. It's the sup norm of the log of the derivative. And immediately we can see that we get a non-trivial space here because this Moebius space MZ is proper. So that means in particular, if Z is an infinite compact space, then the Banach space CZ is never proper. So that means that the Moebius space MZ is not isometric to CZ. It's a proper subset of this UMZ. Okay. So we get a non-trivial space here. And the first question is, does this space MZ contain any points apart from rho naught. So it's not easy to see that you can construct. So it's easy to construct separating functions, which are Moebius equivalent to a given rho naught, but it's not clear that they satisfy the antipodal property. Okay. So how do we get antipodal functions, which are Moebius equivalent to rho naught? So we do that as follows. So let tau be a continuous function on Z, and let rho be the corresponding separating function E of tau, so that the log of the derivative of d rho by d rho naught is equal to tau. Then rho is antipodal if and only if, for all xi in Z, the maximum over eta in Z of rho xi eta is equal to 1. This is the antipodal property. And this is if and only if the maximum over eta in Z of the log of rho xi eta squared is equal to 0. Now you look at the definition of rho, and from this log of rho xi eta squared, this is equal to tau xi plus tau eta plus log of rho naught xi eta squared. So the maximum of this quantity over eta should be equal to 0. So this motivates the following definition. The discrepancy of tau is defined to be the continuous function d tau on Z, given by, so d tau of xi is defined to be the maximum over eta in Z of tau xi plus tau eta plus log of rho naught xi eta squared. Okay. So as we've just seen, the separating function rho equal to E of tau, this is antipodal if and only if the discrepancy d tau is identically 0. Okay. So the antipodal functions correspond to continuous functions whose discrepancy is 0. Okay. So we want to construct continuous functions whose discrepancy is 0. Okay. Now we can look at the map. Tau goes to d of tau. So this is a map from the Banach space CZ to CZ. We can think of this as a vector field on the Banach space CZ. And then in fact, one can show that this is a 2 Lipschitz vector field on the Banach space CZ. Now we have a vector field, and we can look at the following differential equation on the Banach space CZ, which is what we call the antipodal flow. So this is the ODE on CZ given by ddt of tau t is equal to minus the discrepancy of tau t. Okay. So this is an ODE in this Banach space. And then we have the following theorem. For any tau naught continuous function on Z, there is a unique solution tau t of the antipodal flow, which starts from tau naught and which is defined for all positive time. Okay. So we have long-term existence of solutions to the antipodal flow. And moreover, tau t, as t tends to infinity, the limit exists in the Banach space CZ, and we call the limit tau infinity. So solutions converge to a limit as time tends to infinity. And moreover, the discrepancy of the limiting function tau infinity is 0. Okay. So therefore, we get a function whose discrepancy is 0. So we can construct an antipodal function from it. Okay. So this leads to what we call the antipodalization map. So this is a map P infinity from the Banach space CZ to the Moebius space MZ. Tau naught goes to E of tau infinity. Okay. So that means you start with tau naught, you run the antipodal flow till let time tend to infinity, take the limiting, it converges to a limit tau infinity whose discrepancy is 0, and then take the corresponding separating function such that the log of the derivative of that separating function is tau infinity. That will be an antipodal function. Okay. So this gives a map from CZ to MZ, and this map is the main tool to study this space MZ. So using this map, we can show the following, that the space MZ is unbounded. So in particular, it's non-trivial. It's not just a singleton. We do get lots of non-trivial points in MZ. We can show that, moreover, it is contractible. So like a cat minus one space, this space MZ is contractible. It is proper, we've already stated. And using this antipodalization map, we can construct geodesics in the space MZ and show that it is a geodesic space. And moreover, we can show that it is a geodesically complete space. Okay. So now we can define a compactification of this space MZ by taking the disjoint union with Z and let that be M hat of Z. So then there is a topology on this union M hat Z such that M hat Z becomes a compactification of MZ, which we call the maxima compactification of MZ. And the topology on this compactification is the following. A sequence rho n in MZ converges to a boundary point xi in Z if, first of all, the distance from rho n to the base point rho naught goes to infinity. And if we look at the set of maxima of the derivative d rho n by d rho naught, then these compact sets, they shrink to the singleton xi as n tends to infinity. So this defines a topology which makes this M hat Z a compactification of MZ. And the boundary becomes Z. Okay? And then you can show that any point rho in MZ and given any point xi in the boundary Z, there is a geodesic ray gamma which starts at rho and which converges to xi as t tends to infinity. So you can join any point inside MZ to any boundary point of Z by a geodesic ray. Okay. Now, let me just recall what is the Busemann cocycle for a good Gromov hyperbolic space X. So this is a function on X cross boundary X defined as follows. So B of X comma Y comma xi is defined to be the limit as Z tends to xi of the distance xz minus the distance yz. Okay? So this limit exists for a good Gromov hyperbolic space. Okay? It just needs that the space is boundary continuous. And why are we interested in the Busemann cocycle? Because recall the visual quasi-metrics for a good Gromov hyperbolic space, these are Moebius equivalent to each other. So we can talk about the derivative d rho y by d rho x. And it turns out that the log of the derivative d rho y by d rho x at a boundary point xi, this is given by the Busemann cocycle, b of x, y, xi. Okay, so this is well known for cat minus one spaces, but it also holds for boundary continuous Gromov hyperbolic spaces. Okay. Now, come back to antipodal spaces. So suppose Z is an antipodal space and MZ is the corresponding Moebius space. So then we can define a Busemann cocycle as a function on MZ cross Z by the same formula, B of rho 1, rho 2, comma xi is the limit as rho tends to xi in the maxima compactification of the distance rho 1 rho minus the distance rho 2 rho. Okay. And then we have the following theorem that just like for a cat minus one space or a good Gromov hyperbolic space, for any rho 1, rho 2 in MZ and for any xi in Z, the log of the derivative d rho 2 by d rho 1 of xi is equal to the Busemann cocycle b of rho 1, rho 2 xi. Okay. So these Moebius spaces for an antipodal space Z, they behave very similarly to cat minus one spaces. Okay. And even more so, this compactification M hat Z, this is boundary continuous in the following sense. For any rho in MZ, the Gromov inner product from MZ cross MZ to R, this extends continuously to the compactification M hat Z cross M hat Z. Okay. And then we have the following theorem that for any rho in MZ and xi eta in Z, rho of xi eta is equal to e to the minus Gromov inner product of xi eta with respect to rho. In other words, every element of the Moebius space MZ is visual. It comes from the Gromov inner product of the space MZ with respect to the boundary Z. So it behaves just like very similar to a cat minus one space. So, okay. Now we can come to the main theorems. So we have the following equivalence between antipodal spaces and the corresponding Moebius spaces. So let Z1, Z2 be antipodal spaces. Then any Moebius homeomorphism F from Z1 to Z2, this extends to an isometry capital F from MZ1 to MZ2. Okay. And this is easy to see actually. The isometry is nothing but push forward of antipodal functions, right? Since F is Moebius, if you push forward an antipodal function on Z1, you will get an antipodal function on Z2, which is in the same Moebius class. And so that will be the isometry. It's just push forward of antipodal functions. This is the isometric extension. And the converse is a bit harder to show. Any isometry between the Moebius spaces, MZ1 to MZ2, this extends to a Moebius homeomorphism F from Z1 to Z2. Okay, so now let Z be an antipodal space. Now we can consider the case where the antipodal function is quasi-metric. So if some element rho of MZ is a quasi-metric, then it's easy to see from the geometric mean value theorem that in fact all elements of MZ are going to be quasi-metrics. Okay? And in this case, we simply say that the antipodal space Z is quasi-metric. Okay, so then we have the following theorem. Let Z be an antipodal space. Then Z is quasi-metric if and only if the Moebius space MZ is Gromov hyperbolic. Okay, so the antipodal space is quasi-metric if and only if the Moebius space MZ is Gromov hyperbolic. And in this case, the Moebius space MZ is a good Gromov hyperbolic space. So let me recall, good means proper, geodesically complete, and boundary continuous. And moreover, there is a canonical Moebius homeomorphism F from the boundary of MZ to the space Z. Okay. So what does that mean? That means this space MZ that we've constructed is a good filling of the quasi-metric antipodal space Z. Okay, so every quasi-metric antipodal space has a good filling, this Moebius space MZ. Okay. Now I can define what is a maximal Gromov hyperbolic space. So let X be a good Gromov hyperbolic space. We say that X is a maximal Gromov hyperbolic space if X is the unique maximum element of the partially ordered set F del X. Okay, the set of good fillings of the boundary of X. So what does that mean? That means that Y is less than or equal to X for all good fillings Y of boundary X. So explicitly, what does that mean? That means that whenever Y is a good Gromov hyperbolic space with a Moebius homeomorphism F from boundary Y to boundary X, then F extends to an isometric embedding from Y into X. So every filling of boundary X embeds isometrically into X. So then we say that X is a maximal Gromov hyperbolic space. Okay. So are there any examples? Well, yes, any proper geodesically complete tree is a maximal Gromov hyperbolic space. Okay. So this, we can show this. And now we have the following theorem. Let Z be a quasi-metric antipodal space. Then MZ, the Moebius space MZ, this is a maximal Gromov hyperbolic space. Okay. So this gives us many examples of maximal Gromov hyperbolic spaces. And if Z is an ultrametric antipodal space, then MZ turns out to be a proper geodesically complete tree. Okay, so this recovers the tree constructed by Barer and Schroeder. This Moebius space is the tree constructed by them for an ultrametric antipodal space. And now we can show the following. Let X be a good Gromov hyperbolic space, and let delta be such that all triangles in X are delta thin. Then we have a map from X into the Moebius space M of del X, which sends a point X to the visual quasi-metric rho sub X. This map, it turns out, is an isometric embedding, and the image is 7 delta dense in M of del X. Okay. Moreover, this isometric embedding is surjective, so the map becomes an isometry from X to M of del X, if and only if X is a maximal Gromov hyperbolic space. So in other words, if X is a maximal Gromov hyperbolic space, then X is isometric to M of del X. So what that means is that, in fact, all maximal Gromov hyperbolic spaces are of the form M of Z for some quasi-metric antipodal space Z. Okay. So now we have the following theorem. So let F from boundary X to boundary Y be a Moebius homeomorphism between boundaries of maximal Gromov hyperbolic spaces X, Y. Then F extends to an isometry from X to Y. Okay, so we have a positive answer to the Moebius problem, the problem of extending Moebius maps to isometries for these maximal Gromov hyperbolic spaces. Okay. And generalizing the theorem of Barer and Schroeder, which gave equivalence of categories between ultrametric spaces and trees, we have the following theorem, that the functors X goes to boundary X, and in the opposite direction, Z goes to MZ. These give an equivalence of categories between maximal Gromov hyperbolic spaces, where the morphisms are isometries, and quasi-metric antipodal spaces, where the morphisms are Moebius homeomorphisms. Okay. So from ultrametric antipodal spaces as boundaries, we've come to a much larger class, namely quasi-metric antipodal spaces. And in place of trees, we now have these maximal Gromov hyperbolic spaces, okay, which have this universal property. So they're canonically associated to these quasi-metric antipodal spaces. Okay. And so just as a final, to finish, let me just, give an application of this, these Moebius spaces, these maximal Gromov hyperbolic spaces, to the problem of extending Moebius maps to isometries for manifolds. So suppose X, Y are complete simply connected Riemannian manifolds with pinched negative curvature in between minus b squared and minus 1. So then let F be a Moebius homeomorphism from boundary X to boundary Y. So then we know that F star from M del X to M del Y, this is an isometry. So this is just, again, push forward of antipodal functions. Okay, this isometry is just push forward of antipodal functions. And now X is sitting inside M of del X, and Y is sitting inside M of del Y. Okay. So then we have the following theorem, that the following are equivalent, that the Moebius map F extends to an isometry between the manifolds, capital F, from X to Y. Okay. This is equivalent to the following, that the isometry F star sends X to Y. Okay, the isometry is going between the thickenings, the bigger spaces from M del X to M del Y. We want the isometry F star to send the subspace X to the subspace Y. Okay, so this is equivalent to F extending to an isometry from X to Y. Now this is equivalent to the following, we have a function R on the product X cross Y given by the following: R of X comma Y is the distance between F star X and Y. Okay. So this is the distance in the Moebius space M of del Y. Okay. So this function on this Riemannian manifold X cross Y, if this is convex, then F extends to an isometry from X to Y, if and only if. Okay, so convexity of this function on X cross Y is equivalent to extension to an isometry. And we have a last, well, convexity of a function on a manifold means that the function is convex along geodesics in X cross Y, and geodesics in X cross Y just correspond to pairs of geodesics in X and in Y. So we want this function to be convex along all pairs of geodesics. But in fact, we don't need to look at all pairs of geodesics. This is equivalent to the following. You just need to look at parallel geodesics. So for any pair of geodesics alpha in X and beta in Y, such that F star composed alpha is parallel to beta, the distance function d of F star alpha t comma beta t, if this is convex, then F extends to an isometry from X to Y. Okay, so all these are equivalent. So these are just, I mean, proving either 3 or 4 is still hard. So these are really reformulations of the problem of extending to an isometry. And what we're able to show up to now is that we want to show convexity of this function on X cross Y. We're able to show that this is semi-convex. Okay, so semi-convex means that restricted to any geodesic, the second derivative is bounded below by some negative constant. Okay, in the weak sense, the second derivative is bounded below. Okay, so okay, that's all I wanted to say. So thank you for listening. Okay, so thank you.